excellent talks you have had yesterday and today. I guess if I asked you for a show of hands on whether you agree with the question posed in the title, I would suspect the majority of you would say, yes, it does. But, we don't do physics by democracy, which is why I've been invited here to argue for the opposition. And I guess what I would like to do is to go back a little bit, step back from the wonderful evidence you have heard about and all the impressive results that have come in the last few years, which are indeed very hard to dismiss, and suggest that we do need a paradigm shift in cosmology, but perhaps not of the kind that we have been undergoing, which has very rapidly, within the space of a few years, converted a question like that in the title, which, let's say, 10 years ago would have been interpreted in just the opposite way. People would have said it's a very speculative notion, to something which is basically the establishment fact today. So I know that many people here perhaps are already convinced that dark energy exists. So my talk is really directed at those of you who are perhaps still debating the matter, would like better than 3 standard deviation evidence, especially people from more particle physics end of things. And what I'll try and do, since I have only half an hour to match the several hours of talks that have gone before me, is to try and summarize that. There is a paper on this coming out. I had thought it would come out this morning, but actually it will come out tomorrow morning on the archive, and you can look at that for details. So let's remind ourselves that it's not just enough to have good data, you have to interpret it in the context of a model. And the model that we use goes back to 1930s, quite a long way back. And that's based on at the time there was no data, and as you know, we chose a metric which was maximally symmetric simply because there was no further consideration that played a role at the time. And therefore, we chose the simplest possible metric, and we chose the simplest possible theory of gravity based on coordinate invariance. I mean, you could construct a more elaborate version on, say, conformal invariance as Wilde did, and so on. But these ideas have stood the test of time, and they have enabled us to construct, right then, a model of cosmology which has as few parameters as possible, which is, of course, appealing, but without the compelling force that the parameters have on the particle physics side, where they're based on Lagrangian restriction. Here we are assuming the symmetries. We have not tested the symmetries. So, for example, the exact homogeneity, which is built into this metric here, has not really been tested as much as some of the predictions of this model. And I'll come back to that later. So, of course, when you plug these equations into the metric, you get the usual Hubble equations. And what I would like to emphasize is that this model necessarily has dark energy, because the symmetry of this equation allows you to add any term proportional to the metric, right? That's the cosmological constant. And that will, of course, then permeate through into the dynamical equations and into this omega lambda. So, by construction, this model has dark energy. And you can see that more clearly in this nice Dalitz's-like plot that was constructed by Mehta Bakal and collaborators, where you look at the sum rule, the sums of these 3 energy density components should add up to 1. And it's quite clear that if you try and estimate this quantity by trying to measure these 2 and take it away from 1, you're always going to get some number, simply because you can't measure these very, very precisely, but at least that was the case. And the indications for lambda for many years, I mean, the indications for lambda are not just in the last 8 years. Those who know the history of cosmology will know that it has cycled through many, many reincarnations. Many of the early indications were, I believe, because of using the sum rule and not allowing for the uncertainties in the measurement errors. I think what turned the tide was that about 8 years ago now, as I mentioned, Steinhardt, Ostreicher, Bakal et al. Put together these 3 lines of evidence. One from the supernovae, which is still dominating the business today, where you compare local objects with distant objects. You don't actually see things in between, and that's still a big gap that needs to be addressed, and there are ongoing surveys and future surveys which will try and fill in that gap, which is, I think, crucial for reasons that will become clear. And that gives you an indication for acceleration of the universe. What you actually measure is the luminosity distance, and you find objects are about 30% further away than you think they ought to be in a decelerating universe. So it doesn't actually directly measure acceleration, you measure the luminosity distance. What has proved to be robust is the measurement of an angular distance, the scale of fluctuations on the last scattering surface, and that at that time gave a rather weak indication for flatness. As we just heard, this has got even better. But that was pretty impressive all the same. The last argument, I think, is the weakest of all. That was based on a measurement of the matter density. Many lines of argument. This one relied on the evolution of the numbers of clusters, which it was argued are not evolving as fast as they would in a high-density universe. The evolution seems to have stopped, suggesting that it's a low-density universe. This argument is perhaps the flakiest of all, but anyway, when you put it all together, you converge on the lambda CDM model, and that is, I guess, the point at which a lot of people started taking it seriously. But we also know why it caused anguish in other circles, because we know that that value of omega lambda, which is of order 1, corresponds to an unnaturally small vacuum energy. And we also know that this raises two problems. The old problem of the cosmological constant, which was there right from the beginning, and this new coincidence problem as to why this quantity has become of order the matter density today. Now, there's a lot of activity going on in astronomical circles trying to evaluate more detailed models. In my view, they're all very, very, very fine-tuned, not just the evolving scalar fields, which must have, by construction, a amplitude which is 30 orders of magnitude larger than their curvature, because if the curvature was not so small, these fields would not be damped by the Hubble expansion today, and they could not therefore be put into slow roll. So they are extremely fine-tuned, and so are models where you modify gravity on large scales. This is an example, apart from the fact that these models tend to be sick. Theoretically, they have ghosts and other problems on small scales. They are also fine-tuned because you are putting in the scale at which the gravity is modified, becomes 5-dimensional, etc. by hand. So therefore, conceptually, I don't believe that they offer a substantial improvement over just a bare cosmological constant. Now, the most natural solution to the coincidence problem would be if you had a theory that said lambda is always of order h squared. Okay? So it's not just of order h naught squared today, it has always been of order h squared. Now, that is actually trivial to dismiss, because if that was the case, then you can look at the Friedmann equation. The left-hand side is h squared, the right-hand side is lambda. If lambda was proportional to h squared, you can just absorb it on the left, and that is equivalent to just a renormalization of Newton's constant. Okay? And we know that Newton's constant as measured in the lab is the same as that you measure in the heavens, within a few percent. Right from nucleosynthesis, you get it to be within 5%, you can make it better. There's a recent paper saying it's within 1%. So that idea is ruled out, and therefore I would conclude that there is no natural explanation for the coincidence problem. You cannot have a model which gives you lambda of order h squared, which people from quantum gravity, etc. have been thinking about. So the question that I would pose is, we are seeing today lambda of order h naught squared. Is that because we have the observational sensitivity to see just that number? If it was much more, we would not be here. If it was much less, well, that is a possibility that I'm looking at. But this is in fact where our signal to noise is about 1, and that's where most of the indications are. Now, we've seen a lot of pretty pictures of galaxies and numerical simulations and so on, and people helpfully point out that the colored dots are galaxies for the benefit of string theories. So I thought I would show a nice picture of a Lagrangian for the benefit of the astronomers, and remind you why this number is so ridiculous. Okay? So what we have today is a Lagrangian, a standard model as we call it, which is based on symmetries that have been experimentally tested. They have not been imposed by fiat, as in the case of the cosmological model that we use. And therefore, we know every term that should be allowed in the Lagrangian by the symmetries, and they are there. You have to put them in. So one can divide them into 3 classes. Okay, you can have the renormalizable terms, which are written symbolically here, and these are the ones that we can actually measure in the laboratory, although it is fair to say that we have not seen anything to do with this. This is the Higgs field. We have not tested this term. We have done, of course, very fine tests at the quantum level on the gauge terms, on the fermions. We still don't have an understanding of the fermion mass problem, but that's where the action is in particle physics. But the Lagrangian does allow you, the symmetries do allow you in this effective field theory philosophy to add an infinite series of other terms which reflect the new physics beyond the standard model that we don't know about. And all we know is that they'll be suppressed by powers of the cutoff and powers of the scale beyond which the new physics comes in. And these might correspond to all kinds of new physics. For example, that could be a neutrino mass, this could be a proton decay, flavor changing current, etc., etc. We don't see these things, or we do see them at a very small level like neutrino mass, so we know that this lambda is large. But that raises the problem that there is another set of terms we can also allow, which are these two here, and they are proportional to powers of lambda. Okay? There are just two such terms, and their effect is exacerbated as you make lambda larger and larger in order to suppress these terms and be on the safe side. You run into problem with those. Now that term there, this is the famous notorious Higgs quadratic mass divergence. Okay? And to solve that problem, physicists have invented 100 new parameters. That's supersymmetry. Okay? So Max Tegmark talked about the number of parameters and how now we have 6 parameters in the standard cosmology to act as the parameters in the standard model. The point is that we have certainly had to jump from the few parameters necessary to describe these to 100 extra parameters to explain that. Okay? So you can't tell me that the other term in there, which is the cosmological constant, that you're going to get away with explaining that or parameterizing that by one number. Okay, that just seems physically implausible. Now this term, of course, has no effect on laboratory measurements. The people at LEP, LSC don't care about it. It couples only to gravity. And that is the fine-tuning problem, that's 60 orders of magnitude bigger than the one that you have experimentally seen. Okay? So this, I think, is important to appreciate before starting to play games with lambda, quintessence, etc. But of course, we are driven by data. We are empirical people. We believe what we see on the sky, and what was really impressive, what was the breakthrough, was this beautiful picture that Lyman talked about, which convinced many people that indeed we are seeing evidence for dark energy, because of course it gives these very precise measurements. Of course, these things are all coupled together, but it does make a very impressive presentation. But actually, if you look at it from a informational point of view, this fit is not really that good, because there are points that don't lie on it and they have tiny error bars, so the chi-square is actually not that good. It's this has improved in WMAP 3. WMAP 1 had only a 3% chance of fitting the lambda CDM power law model with the scalar spectral index, which was slightly steeper at the time. And even this one has only a 7% chance of being right. So we are really, although that is not enough reason to get worried, one must keep these things in mind, that it is not as good a fit as the standard model of particle physics is to the data. Now, the first question that arises is, how do you measure lambda from this? Because we all know, this is from Wayne Hu's work, you know how the baryon density and the matter density and the curvature, etc., affect the positions of the peaks and the relative amplitudes. It's all beautiful classical physics. But lambda has no effect because it's completely negligible at the time of last scattering. It only has a very mild effect on the distance to the last scattering surface. That's the only effect of lambda. So therefore, you have to use other data in combination with the CMB to try to extract lambda. CMB by itself does not give you lambda. So these are various measurements that we have heard about. But I want to emphasize that these measurements are very sensitive to some of the underlying assumptions, the priors. The prior of, for example, a power law spectrum from the fluctuations, not correcting for logarithmic or even worse corrections that might be there. You make assumptions for the dark matter, for example, that it's purely cold, non-interacting, and so on. There is the Hubble diagram. I mentioned it measures DL, with the calibration is local, so the insensitivity as to whether we really are in a homogeneous universe, could we be in a region which is not reflective of the average. The baryon acoustic peak measures an angular diameter distance, same problem. They depend on homogeneity. And clusters, actually, it has become apparent in recent years that the scaling relationships for clusters are violated, and therefore some of these early arguments need re-examination as to whether they still indicate a low density universe with lambda. So let me give an analogy for the particle physicists here as to what we are really seeing when you look at these beautiful pictures of galaxies in the microwave background. We are seeing a scattering experiment. The beam in this case are the fluctuations presumably from inflation. That's our best theory to date. We don't have a model for inflation. There's no standard model anyway. And we usually assume that this fluctuation is purely adiabatic and roughly scale invariant. Okay. For good reasons. This is a good starting point. The target we take to be dark matter, but we assume it and have done so for some time to be purely cold. There could be a hot component. The dark matter might have interactions. It may not have the simple properties that are assumed for studying the growth of the fluctuations in the dark matter. And we see all this to a detector for which you don't have a Monte Carlo like Atlas or CMS or whatever. We model it with this few number of parameters. That's the simplest possible model we can have, and therefore what we interpret will be subject to the same assumptions. The signal we see over roughly 80 folds of inflation. That's a range of 10,000, but that's where there has been most progress. But I think you will agree that given all these unknowns, we cannot possibly determine the properties of both the beam and the target with an unknown detector. Okay? We have to make some assumptions to make progress, and those assumptions, of course, have a fancy name. They are priors in the Bayesian approach that lends itself so naturally to cosmology, because you can't repeat the experiments. You better do Bayesian statistics. Unlike among the particle data group, we believe in frequentist statistics because we can repeat the experiments. Here you can't. So let me give you an example of how these degeneracies can affect your parameter extraction and provide a new perspective perhaps on this precision cosmology that we are all asked to embrace. So in the 80s, I've been doing this for some years now. I recall if Satya and company were in the first standard whole dark matter model, they always assumed the Harrison's and Lowy spectrum because that's the simplest possibility, and the early work on inflation had suggested something like that. At that time, there was no sensitivity to log corrections in K and so on. So that's what they took. But of course, we know from the work of Andre, Lente, Slava Mukhanov and others that we have deviations from scale invariance which will go as powers of log K, and this will give you a tilt to the spectrum. We can calculate the tilt. So these are not predictions in the sense that we don't know that inflation actually was driven just by a single field in slow roll, but if it was, then you would expect a tilt below 1, which is of a few percent off below 1. And that is indeed consistent with what you see in the WMAP data. Okay? But as I emphasized, that model fit is poor. There are glitches. There are points that don't fit any power law assumption for the primordial fluctuations. And therefore, one should, I think, be cautious about saying that the data confirm the prediction of inflation. Okay? There were many predictions of inflation. It is unwise to just pick out the one that your present model you think now fits and not bother to look at the fact that the fit is not really that good and is perhaps suggesting that there is more physics. And indeed, it was noticed already, in fact, well, Andre, who is here, invented both the new inflation and hybrid inflation, so I'm sure you won't mind my referring to both. It seems unlikely that there is only one field involved in inflation. Supposing a second field ended inflation, it was not due to the steepening of the potential, but due to the dynamics of some other field in the inflating background. Then the spectrum does not have to have this tilt. You can interrupt it very close to where it is really flat. But why stop at one field? In general, there are many, many, many fields. What is their effect on the evolution of the inflator? Right? What I'm going to discuss in the rest of my time is the possibility that the situation as motivated by a concrete particle physics model was just that there were many fields, they influence inflation, and they generated features in the spectrum for which we have some observation and indication. And the test will be to ask, does this model fit the data better in terms of chi-square than the parallel Andersonian model? And I claim that it does. Okay? So that's what should interest the CMB people here, because they are empirical, they have no prejudice about models beforehand, they are just asking what is the best thing that fits the data. So this concrete model is one that is in the context of the best effective field theory we have today, which is supergravity, and for the astronomers, let me point out that this theory, which has been also around for 25 or so years, is based on the idea that we live in the standard model lives in the so-called visible sector, we also interact with the so-called hidden sector where supersymmetry is broken, and this coupling is purely gravitational. Okay? And the effect of this, of constructing inflationary models in the context of supergravity, where the inflaton typically is in the hidden sector and therefore uninfluenced by radiative corrections, is that, as was noted, the potential of all this, any field which is initially flat, i.e. has vanishing potential because of supersymmetry, is actually lifted during inflation because supersymmetry is broken by the vacuum energy. And it's of course also lifted by higher dimensional operators which are there in the effective field theory description. So the net result of a long discussion is that all these flat direction fields which live in the visible sector, which are called here rho, will undergo phase transitions during inflation if the initial conditions are such as to start them at the origin. So in this picture, what we see on the sky today is not the primordial inflation, it is the last episode of inflation. There might have been many. There must have been an initial one because inflation does not solve the homogeneity problem. You have to have a flat patch to start with. So you might speculate as to how we got from the Planck scale down to there, but that's the framework in which we're doing this. And well, let me just flash through this because I want to actually get to the data fitting. And the point is that we can make a precise calculation of how these fields evolve. There's standard tools of thermal field theory. You can work out how the inflaton mass is altered because these fields initially attract at the origin because of the thermal barrier. When inflation starts, the barrier disappears, they zap to the minimum, they get a large breadth, therefore a large mass. The inflaton couples to gravity through these fields, so it also gets a jump in its mass. And it's a jump in the inflaton mass that you will see by solving the Sasaki-Bukhanov equation will give you a certain step in the spectrum and oscillations. And of course, all this is going to be relevant only if the last phase of inflation lasts just long enough to create the Hubble volume. Because if these things happened very long ago in the beginning of inflation, then if inflation went on for hundreds of E-folds, they're still out there. We still haven't grown big enough to see them. But the indication from the data is that the last phase of inflation created just about a space as big as the present Hubble volume. So let me show you what happens when you do this calculation, when you ask what happens if the inflaton mass changes suddenly over 1 or 2 E-folds because of some background field dynamics. What you get is a jump in the amplitude of the primordial perturbation followed by rapid oscillations, which are because these fields are damping in the minimum because of the Hubble expansion during inflation. And you compare that with the Harrison-Zeldovich spectrum. Okay? So this is telling you how much is the jump in the inflaton mass corresponding to all this. Now this is some work that we did a few years ago based on that model that I showed you. And remember this picture and compare it now with what you get when you reconstruct the primordial spectrum of fluctuations, assuming lambda CDM. You can do this procedure by the raw data, you invert it, you find something very, very similar. Okay? You see a step in the spectrum followed by what look like oscillatory features. These are driven by the glitches, these are driven by the low quadrupole, octupole, etc. And let me point out that, for example, this is the power law from WMAP1, 1995 now is very similar, whereas this is the actual data. So the power law fit is a very poor one, as you can see, and what we see are these oscillations which are suggestive of what we saw in the physics model that I gave you, and it also seems to cut off at the scale of the present Hubble radius. So many people have noticed it. This is some work by my colleagues in Oxford. I think this method was first pioneered by Tarun Sauradeep and collaborators, non-parametric Richardson-Lucy inversion, which is much more sensitive than pinning in K, which was what was being done before. So we have done a full, bells and whistles, Markov-Chen Monte Carlo exploration of this model. That's what is going to come out tomorrow morning. You can welcome to have a look at it. But the bottom line, let me not bore you with all the details. The bottom line is the cosmological parameters do not change very much even if you let the position of this step and its amplitude and so on vary all over the place. Okay? But that's not surprising because to recover that picture you assume lambda CDM, so it's not surprising that you get lambda CDM back when you use that as the input spectrum. But let me talk you through something which is more interesting. Once you have opened the Pandora's box of accepting that the initial primordial spectrum does not have to be a power law, it does not have to be smooth, it could have features in it, it could still fit the data just as well as the power law, in fact better. Why not have more than one phase transition? There are many of these flag direction fields, they all evolve on roughly the same time scale, they might reach their minimum very shortly after each other. And if that happens, then you can create a spectrum that looks like that. So this is now the 0.95 power law of the standard concurrence model, and I can create a spectrum that looks like that. This is due to two phase transitions in rapid succession. One with the upward mass change, one with the downward. Of course, you don't have to believe my model. Just take a Gaussian or Lorentzian or whatever you like with one parameter and put it there. That's all I'm asking you. You take that spectrum and you put it into the data, and you find that you can now fit the WMAP data as well as the standard power law model. In fact, slightly better, because this model has no dark energy, it has no integrated Sachs-Source effect, so the low multipoles are a bit lower. Not that it makes much difference because cosmic variance is very large there. But I want to ask you, if you look at that picture and you are asked to pick out which model is a better description of the data, you would have to agree that they provide an equally good description. And yet that model has zero dark energy. You are not talking about a deviation from W of 0.1 or 0.01. I'm talking about a deviation of 1. Okay? The price you pay in order to fit the position of the first peak is that you need a low Hubble parameter, because it goes as omega matter h cube. The degeneracy line that is shown on the WMAP papers, which seems to exclude omega matter of 1, I believe is calculated on the assumption that the spectrum is featureless, so it is not a purely geometric degeneracy. You can also fit the TE data. Okay. Now,
if you will change the spectrum,
yes,
because you
right, yes,
yes.
Yeah, I'll show you the plot in a second. We have done a Markov cell Monte Carlo of this as well to answer precisely that question. It of course varies around that by about 5 kilometers per second. Now let me just point out to you that this is of course, as everybody knows, not consistent with the Hubble key project value, but the Hubble key project value is actually smaller, as been noted by many people, from what you measure when you make measurements very deep. When you make measurements using gravitational time delays, they go up right up to here. Hubble key project is right there. It goes out only up to a few tens or thousands of kilometers per second. But these strand loops are referring to time delays from lenses, which are going out much deeper. And so the best fit, this is from a paper with Michael Rowan Robinson, who knows a lot more about the Hubble parameter than I do. And we pointed out in that paper that actually the best fit is an Einstein de Sitter model with a Hubble of around 60. Of course, these data have large systematic uncertainties, but our low H Einstein de Sitter model is also a poor fit to the data, okay, as is lambda CDM, if you take into account all the Hubble key project data. So neither of these models is a good fit to the data or to the indications. So it raises a question, is it possible that we are measuring a higher Hubble parameter because the universe is expanding faster in our neighborhood than it does globally? So this is an idea that was actually proposed by some of the key people in the supernova game, Adam Rees, Kirchner, etc., Zehavi and Deckel. They pointed out some years ago that, well, they gave it a nice name, Hubble bubble. If you are in a Hubble bubble, then you can actually explain a lot of things. You can understand why the long, deep measurements are lower than the local measurements. You can understand, for example, why you seem to get low values of omega when you measure locally, etc. And there are also other issues to do with the peculiar velocity field. But I'm just trying to tell you that this idea has been around in the astronomical community. Just 2 weeks ago, there was a paper from the supernova cosmology people revisiting this, and they point out that the issue is a little complicated because the way that they correct for extinction by dust around the supernovae is degenerate with the issue of whether this bubble actually exists. But it is very exciting that if this is actually there, then you might actually understand this peculiar alignment that people keep asking about. This is from the work of Dominic Schwartz and collaborators. And Joe Silk and Inoue, who is a student of Tomita in Japan, who has been looking at this limit Tolman models for a long time, points out that in principle, it's complicated. I should not give you the idea that they've solved the problem, because because this alignment is not an axial alignment, it's a planar alignment. It's very hard to do by just being off-center from a void. You can't do it with a simple model. You have to get more complicated. But it is interesting that it's feasible to explain at least the amplitude, and I think more work needs to be done on that. But you will ask me, well, what about the supernova data? You know, that's the thing that started this business in a sense back in the late 90s. This Lemaire-Torban model, which was introduced only a few years after Friedman Robertson Walker, because these gentlemen who, after all, are also famous cosmologists, and Lemaire has a hand in both, recognized that assuming complete homogeneity all the way from here to the Hubble radius is an unwarranted assumption. There wasn't the data. There still isn't the data, in the sense that this issue has been looked at much less, well, certainly with much less intensity than some of the other things that we hear about, like cosmological parameter estimation to 0.001% or whatever. Right? And so there has been some recent work on that. It's a pity that Reza Mansouri, who I think was meant to be here at this conference, could not come. But you can start asking, of course, there are, in this model, there's an arbitrary radial function which you have to assume and so on. So it's not that there is a definitive prediction. But if you look at the supernova Hubble diagram, so this is the goal set, okay, you find that although most of us would accept that the Einstein de Sitter model is ruled out by the data, it is ruled out by the data, and lambda CDM provides a better fit. This blue line in the middle is the expectation from the Lemaire-Tolman model of a local void. Okay? And I think you will agree that it is encouraging and suggests that, again, one needs to look closer into whether this void is actually there astronomically. Okay? People have looked at it from a statistical point of view, and it's easy to show that such a large void with such a lot of underdensity is extremely unlikely in a CDM cosmogony with Gaussian random, especially if you have a scale invariant spectrum. But the issue is whether we actually happen to be in it, and that's an astronomical question. Now, let me finish by talking about the other data set. So I showed you, what I've shown you is that a model with a bump in the spectrum, that's all it takes to do away with dark energy as far as WMAP is concerned. It does require a low Hubble parameter, but there are interesting issues there that I think need addressing as to whether the Hubble parameter that we measure locally is the global value, or we need to revisit the issue of homogeneity a little more carefully. What about large-scale structure? We saw the impressive results from 2DF, SDSS, and so on. Now, it is well known since the 80s that a pure cold dark matter universe has excess power on small scales if you normalize it to, at the time, it was Cobain or WMAP. But if you have free streaming due to neutrinos, then you can get a good match to large-scale structure. Okay? So this is the SDSS second data release, the power spectrum that they presented. This is the lambda CDM power law, and this purple line that I show here is the spectrum, the same model that I gave you earlier with the bump in the spectrum. It's just as good a fit. Notice that I need a neutrino mass of 0.5 electron volts, which is about 10% of omega, which is much, much larger than the kind of numbers we have been seeing in the literature as having been set by WMAP, whatever is the WMAP bound or neutrino mass. Well, Steve discussed it in detail yesterday. He emphasized the role of priors in extracting the bound. But, seeing is believing. What I'm saying is that for this model to work, we need neutrinos of half electron volt, and over in Karlsruhe, they're building a detector as big as this room, which will measure that as soon as it turns on. They told me, I don't know, in the first, maybe it's not the first 7 minutes of data, as was the case for the Fourier spectrum, but within the first 3 days, they will know if it is half an electron volt. Okay, few years. This model, by the way, has a baryon density, physical baryon density, perfectly consistent with BBL. And because H is low, a lot of people miss this point. Because H is low, you get a omega B, which is about 10%, that will give you a baryon fraction in clusters, which is just about tolerable. It's not completely out of line. You get a value of sigma 8, which is lower than the lambda CDM standard concordance model fit, perfectly consistent with clusters, consistent with peak lensing. So here are some parameter degeneracies we have studied in great detail. The fact that, as in all Markov-Chen Monte Carlo analysis, for example, you can trade off the baryon density against the change in the mass of the inflaton. This is the second step. or it could trade off, let's see something else, the position of the step versus the full dark matter density. We have explored all these. As I said, the details are there in this paper. I won't dwell on them. But to answer Slava's question, this is the one-dimensional likelihoods in this model when you explore the full parameter space of this model with the bump in the spectrum. So the amplitude of the bump is, of course, a free parameter. The position when you put it is a free parameter. You just scan through all the parameters as you do normally, and you construct these likelihood plots of when the chains have converged. And to answer your question, here is H. So these are these different lines correspond to different combinations of data. The one you should be looking at is this blue and the green line. The green line is WMAP, blue line is WMAP plus SDSS. Ignore the purple line because that's the luminous red galaxies, the baryon acoustic oscillation, which this model cannot fit. So that we have to pull it down. But you can see that everything else, as I mentioned, sigma 8 is a bit lower than what you expect in the power law model. The age is okay. So in fact, I really have some notes about this. Yes. So notice that the full dark matter density is actually about 50% higher than the scored precision value from WMAP that a whole bunch of people who are studying dark matter at colliders are inputting into their codes. Okay? So that is how precise their number is. You can get a number 50% bigger. This one here is the sigma 8, which is interesting to astronomers. It is consistent as far as I know with the data. The age is, as I said, perfectly consistent because the Hubble parameter is low, and the value of sigma 8, F nu I've already told you about. You need half an electron volt neutrinos. Okay? So in other words, this model is completely different from all the things you have heard about, and therefore it's interesting to reflect on the fact that it provides a fit to the data which is a chi-square better than that of power law lambda CDM. So chew on that, okay? Or put it in your pipe and smoke whatever. But there is, of course, data that we cannot fit, and that's because of this new stuff. Astronomers are very inventive, and I'm very impressed, as we saw in Mark's talk, how new things are coming up all the time, new tests, new cross checks, new consistency checks. These are essential. And the point is that one must, when doing those checks, keep in mind that if you see a 2 sigma discrepancy, you don't just dismiss it because you don't like it. Whereas in a different context, when you see a 2 sigma support, you say this is great. Okay? It's important to really be open-minded in doing those consistency checks. So the baryon acoustic oscillation is a case in point. As you know, thanks to this tremendous effort on the SDSS team, by sampling a huge volume, even if it was rather sparse, using the luminous red galaxies, they could see this. Well, it is barely detectable, but it's there at about, I don't know, 3 sigma level or something. You see this thing in the autocorrelation function of these galaxies. And this position here is exactly matched by the lambda CDM model. But our model, which is with a Hubble of 44 or whatever, cannot match it because this is really an angular diameter, angular distance measurement. And we have already picked the value of H in order to match the position of the first acoustic peak. That's at 1100. So we can't play the same game again. Okay? We can't again choose a different value of H. So we can't match this. Right? So Einstein-Disitter is definitely ruled out, no question. What I find very exciting is that according to these authors, in this Lemaitre-Tolman-Morley model, which they have looked at, okay, where Hubble is 70 very close to us and then goes to 50 far away, when you work out the angular diameter distance at redshift of 0.35, it's very similar number to that for lambda CDM. Okay? Now, of course, you can break the degeneracy by doing this check at different redshifts and see if the variation of this position changes to the redshift. That can discriminate between models. That has yet to be done. But let me conclude, since I think I've used up my time. I want to leave some time for questions, which I usually have much more material, but today I would like to leave some time. So, well, I think this is true to say that WMAP data are supposed to have confirmed, as we heard from Lionel yesterday, the need for a dominant component of dark energy. And the emphasis is on the word precision. Okay, it kind of sticks in your mind psychologically. Precision data, okay, precision cosmology. But there is a basic problem that we are looking at the convolution of 3 unknowns: the primordial spectrum, the dark matter, and the cosmological parameters, indeed the cosmological model. You can't simultaneously find out all of them, at least at the present level. Maybe in future we can, and we certainly hope to. But from CMB data and combining large-scale structure data, you cannot determine both the spectrum and the parameters. So in other words, different combinations of these two things will give you the same fit. Since in particular we don't know the physics of inflation, right? We have experts on inflation here, but I think they will agree that we don't have a standard model of inflation. And in particular, although it's a reasonable first approximation to assume that the spectrum is scale-free and then work out that lambda CDM then fits the data, you can't invert the argument and that would be circular. You then say that the data confirms the power law lambda CDM model. You assume this to get that. Okay? So you can't do both. At the moment, there are hints for these features in the spectrum, and as I showed you, this has a strong implication for parameter extraction. All you need to do is to put a little bump in the spectrum. I gave you a physical model for that, but you can have your own, and that will allow you to fit the data without dark energy. And the basic point is that there is so much fine-tuning required to accommodate dark energy. I think it provides a lot of motivation for asking if this Hubble diagram, barren acoustic oscillations, etc., can be equally well explained in an inhomogeneous cosmology. So I conclude by saying that the Friedman-Robertson-Walker model has served us very well, but it might be an oversimplified description of the universe. Thank you.
So first I want to thank you for being the devil's advocate. I think it's great, important. And then I want to whine a little bit and say I think that whenever you talk about a model where you don't have a homogeneous universe, like a formal model or a local Hubble bubble, right? The model we should be testing is that plus the Earth is in a random place in this cosmos. And then since it's very unlikely that we're so close to the center of this that we don't see huge order unity CV fluctuations.
Right.
They would be sort of.
You're right. We have to be within 10% of the center, otherwise you'd see a. But of course, the alignments that I showed you, those were generated precisely by the fact that we are misaligned from the center. The fact that if you are more misaligned, then they would be even bigger. Right? So you're quite right. But the point is that a priori that might seem unlikely, but I think if that is really the case, if astronomers tell us that we happen to be so located, then we have to accept that fact as much as we accept that the moon looks the same size on the sky as the sun. It's a priori unlikely, but it is the case.
Just one more point about your second bullet there. I think there's actually reason for some real optimism there. That I think you're saying that we cannot simultaneously measure both the thermal spectrum and the parameters. I think in the future we'll actually be able to do that.
Okay, sorry, I should have qualified that at the present time. Yes.
That's my thought there. Because, for example, if you put in more dark matter, that lowers the CND peaks and it increases the power in the galaxy fluctuation. Whereas if you want to do inflation, you always do the same in both. And also with polarization, when we get better measurements in the future from Planck and other missions, those peaks are out of phase with the unpolarized peaks.
Right.
So we'll be able to actually very nicely separate out and get a measurement of the inflation power spectrum. Doesn't really too much.
No, I agree that polarization is the way forward, but as we know from Lyman and others, that's the next big challenge. The biggest challenge is that right now the galactic foreground is at least 6 times bigger than what you are hoping to see. And I certainly, fervently hope that the challenge will be met, and we will see data coming in from that. So I should have qualified that remark refers to the situation today, and as far as I can see. So I'm really trying to inspire. We need to do that. You are absolutely right. We need to break these degeneracies. And for example, what you just referred to about playing of the amplitude of the power spectrum versus the cold dark matter content, I could insert a third parameter like say the hot dark matter density, and screw that up. I could suppress the matter power spectrum by adding more dark matter. But all these things can in principle be broken if you had more observations from different kinds. And I'm just trying to say that we should be doing that. We should not be resting content that we have solved all the problems already. That's my basic point. Yeah.
Would you like to comment on the recent detections of the late time integrated cycle effect?
Okay, so that's a very good point. The smoking gun of lambda would be the late ISW effect. Okay, it was unfortunate that you didn't see it in the CMB on small l. That was unlucky. And then the question is, can you see it in the correlations of galaxies nearby with CMB? Now, I heard your talk at Imperial College where you said you now had 5 standard deviation evidence for that from the Sloan data sets, right? I was hoping to see that again here, but you didn't show it. What surprised me is that I recall that I think it was Niyaj Afshodli who wrote a nice paper pointing out that you need to measure the redshifts of a few million galaxies to really get that at 5 sigma, because the indications from WMAP1, which was done with the radio sources, and then of course it was also done with X-ray background, etc. Those are a little complicated. You really want to do it with a well-controlled sample of galaxies, and that I understand is precisely what you're doing. If you show me 5 sigma evidence for an ISW effect that varies with redshift exactly as we expect it to for lambda, then I'll buy you a beer.
Well, let's not argue whether it's 3 sigma or 5 sigma.
Oh, no, it's crucial if it is 3 sigma or 5 sigma.
We've shown you the ISW effect has been detected at low redshift, intermediate redshift, and now we've detected it at redshift of 1. And it's all consistent with lambda CDM. So
well,
I'm happy to debate whether it's 5 sigma or 3 sigma, but we see it in many different traces.
You're right that it has been seen, but as I understood the redshift dependence of the effect, I understood from some work by Enrique Gastanaga and collaborators, was not what you expect for lambda. So I'm very interested in the new work that you referred to, and I would like to see that, yes.
Since the talk started with the discussion of theoretical statuses, I would say that for about maybe 25 or so years, we were trying all the time to prove what is theoretical constant magnitude zero. And then in parallel with this, there was another development to try to understand why it is possibly small. And the first line of thought so far did not produce any consistent and model which would explain why it was zero. Whereas the second one, after that once model of strings interior landscape, allows using a converted principle at least within an order of magnitude, say that this will range for possible values of cosmological constants. So once again, what we have right now, no models of cosmological constants equal zero.
Yeah, just a comment on the data, since it came up and we're talking. I mean, the quadrupole is just not well. And WMAP can take full blame for that.
When your maximum likelihood estimate is not anomalously low.
No, and the plot you showed in the 1 in 60 that Max referred to came from the WMAP1 data release. Well, the 1 in 60 was just the alignment.
Yeah.
Here's so we did latitude analysis of the non-order multiples incorrect short releases were played out
It's like George F. Sarkar.
right. And so when you go and we turned it up for the second release, and when you do that, let's just take the quadrupole, for example, and just plot the likelihood, and it doesn't show up in any of those plots you showed, why it's misleading. You just take a constant fire on it and ask what fraction of that is above the best lambda CDM model. It's 15%, which is not that weird. So it really.
Sorry, I didn't emphasize the low quadrupole in anything that I showed.
No, the server didn't at all.
Oh, the inversion.
In the inversion plot.
Right. Oh, I see.
That was based on the first year data and not have the full likelihood.
That's correct, but there is later work by Lassenby and collaborators, Hobson and so on at the Cavendish lab, who have been doing this now with a different method using the WMAP3 data, and the overall feature is what I showed.
I think it's not as pronounced.
Oh, the drop is not as pronounced, yes.
Right. And you can see it's all doing there. You can see the octapole
Yes.
is embarrassingly close to the line, and you see the quadrupole down there, but the false quadrupole is not. So I think it's really, I mentioned yesterday, the alignment,
Yes.
and I'm by no means an expert on the alignment. It's in Angelus.
You're saying this drop is not as prominent in the WMAP3, that's correct, yeah. This was...
Nor is that pump there.
This one?
Yeah.
Yeah.
I know the next one.
Oh, this one.
And it also commented.
Oh, that's the glitch that has gone, yeah, right.
Right, so that's not there.
Yeah.
And it also just take the bottom 20 data points and ask how many are outside the cosmic variance
But Lyman, if you had a plot like this, right, and you had got this from the data, and you had predicted something that looked like that, then surely admitted you would also be intrigued by the resemblance.
No, absolutely. And as I said, as you well know, we played around a lot with different power spectrum.
Yeah.
Because
Yeah.
we were looking for a general fix of the
Sure.
data. So it's entirely well motivated and great.
Oh, absolutely. I'm not disputing that for a moment. No, I completely agree. My point was simply that the qualitatively this kind of steps and oscillations is what you expect from a certain physical process which is calculable. And I find that intriguing. So I'm not obviously trying to sell this. I'm not selling anything.
I just
today,
want to
okay?
get the statement.
So
of
it
what
seems
out
that
there.
there's a bit of more clarification on the data you'll see in this model.
Yes, of course. That's true of all models, not just mine.
No, you're still need some explanation as to why we are sitting in the middle of the Hubble bubble.
No, I said that. No, I don't need an explanation for that. If we are, then that's the way. That's astronomy. That's got nothing to do with physics. Now, we happen to be sitting in the middle of a Hubble bubble. That's the way it is. Well, that's absolutely right. I think I might have deleted the plot in question. Kochenek and Schechter simply point out that you're quite right that if you just take 8 lenses which have the best measured time delays, the mass to light ratio in the lenses determines what the inferred value of the Hubble constant is. If you take mass to light ratio to be that of a typical galactic disk, then you get Hubble of 70. But if you take the mass to light ratio to be that of isothermal halo, then you get 48. Okay. That's the way it goes. Well, I was quoting from the paper. I read that. Yeah. That's where they have non-parametric reconstruction. I know that one improvements. Yes. So I think that needs more looking into more.